Okay, yes, it's recording.
Okay, welcome everyone to the second spring semester meeting of the Joint Israeli Probability Seminar. We're very happy today to have Michael Krivelevich from Tel Aviv University to tell us about expansion in supercritical random subgraphs of the hypercube. Thank you, Michael.
Thank you, Ron. Thanks for this invitation. Glad to be here. Actually, the title is even longer than Ron pronounced it. It's expansion in supercritical random subgraphs of the hypercube and its consequences. And it's a joint work with Josh Erda and Mian Kang. Both of them are from Technical University graphs. Now, since the title is so long, let me give a short explanation to it. So basically, we are looking at the binary hypercube 0, 1 to d. So d tends to infinity. It's an asymptotic study. And we look at bond to edge percolation on it. So we take the edge probabilities to be around 1 over d, but substantially above 1 over d. Namely, we will be in the supercritical region. And then the main focus of ours is actually combinatorial properties of the giant component. It's well known that there is a unique component of linear size there typically, and some things are known about its characteristics, like its order, etc., but not much. And we would like to understand its combinatorial properties. And it turns out, not exactly surprisingly, that the best possible way, or kind of a nice way to access it, is through expansion. And that's what we are studying and getting some results. So what we will derive is typical expansion properties of the giant component. Now, this cube here plays conveniently two roles. First of all, it's a depiction of a binary three-dimensional cube, but also it signifies a randomness we will use essentially as a talk, because we are talking about bond percolation. Very good. So presumably all of you are familiar with the hypercube, but let me give you nevertheless some short introduction. So what's a hypercube? So we look at the d-dimensional hypercube, which I will denote by q to the d. So the vectors or the vertices are binary vectors of length d. And then we connect two vectors by an edge if and only if the Hamming distance is exactly 1, which means they differ in exactly 1 coordinate. So altogether what you get is a graph on 2 to the d vertices. I will denote 2 to the d by n. This graph is d-regular, and this graph is bipartite. And the sides are binary vectors with odd weight and with even weight. So that's a very standard graph. It appears all over the place. So here's a depiction of it. It's actually a depiction of 4-dimensional hypercube. And it's nicely done because what you can see here is two 3-dimensional hypercubes, the one in blue and the one in red, and they are connected by a perfect matching, which is in green, to form a 4-dimensional hypercube. So it's some kind of recursive procedure. Now, there's a lot of studies about the hypercube and properties, and a lot of is known about it. It's a simple graph, but still there's a lot to understand about it, and quite a few properties are known. And what we will be interested in, what will be most handy for us, is the so-called isoperimetric properties of the hypercube. So let me define first some notation. So suppose we have some generic graph G with vertex set V and edge set E. And suppose we have a subset S of vertices. We denote as usually by NGS. And frequently we'll omit this index G if it's clear from the context. So NGS is all vertices in V outside of S, which have at least one neighbor in S, which is naturally called the external neighborhood of S. And we will also be interested in the edge isoperimetry and edge expansion. And for this reason, we will denote by partial GS the set of edges of the graph which have exactly one point in S and another point outside of S, which means those edges are crossing from S to outside S. This is the so-called edge boundary of S. Okay, so here's a picture. We have a generic graph G, which has a set of vertices S. Inside it, we look at the edges emanating from it. The set of edges is the edge boundary of S. And we look at the vertices, which are the other point of those edges. And this set is the external neighborhood of S. That's a very standard notation. Now, one piece of notation, which is perhaps less standard, but it's also quite familiar. So we call a graph G an alpha expander if for every subset of vertices S, whose cardinality is up to half of the size of the vertices, we need to leave some room for sets to expand. So for every set of cardinality up to v over 2, it expands outside by a factor alpha. So alpha you can think about as some constant theoretically, and in our case, alpha will be a function of some other graph parameters like regularity or number of vertices. For best expanders, alpha is a constant, but sometimes we will be talking about weak expanders. Now, what's known about isoperimetry in QD? More or less everything is known. So if I need to summarize it in one phrase, I can say that QD is kind of a decent expander. I've seen much better, but it's quite a decent expander, and it has been used in numerous arguments about QD and its properties. Specifically, let me describe what's known about its vertex isoperimetry, which is perhaps of less importance to us, and about its edge isoperimetry. So for vertex, let me define the notion of a sphere. A sphere is a set which includes a ball of a radius k around the vector 0 and is included completely in a ball of radius k plus 1 around vector 0 for some k. So it's more or less a ball plus some small adjustments. And Harper proved in 1966 that if you look at a set S of size m, where m is anywhere between 0 and 2 to the d, then there's a sphere, as we described before, a sphere inside the hypercube QD, so that this sphere minimizes the size of the external neighborhood among all sets of size m, which means the sphere, or strictly speaking, a ball is the worst expanding set. So the worst example is indeed a ball of radius k. So if S is such a ball, then the cardinality of S is the sum of the k plus 1 first binomial coefficients that choose I, and the external neighborhood of S is the set of cardinality d choose k plus 1. For example, if you choose your k to be d over 2, your ball is of cardinality roughly half the vertices, and the external neighborhood is smaller than that, smaller by a factor roughly 1 over square root. Okay? So it's kind of a decent expander. What's perhaps more relevant to us is edge isoperimetry. And see here we have two results of Harper, and which goes as follows. Since our graph is irregular, to say what the number of edges emanating from any set S is exactly the same as saying how many edges are inside S. So Harper's isoperimetric inequality says the following. If you have a set S of cardinality m inside the hypercube, then it has inside not that many edges, and not that many means at most 1/2 m times log binary log m. And in other words, it says that at least md, which is the total sum of the degrees in S, minus m times binary log m edges emanate from this set. This again types, and the worst example here is actually the subcube. If you fix some t coordinates x1 up to xt to be a1 up to at respectively, then we get a t-dimensional subcube, and for this t-dimensional subcube, this estimate of Harper becomes sharp. So it's kind of a decent expander, and we understand quite a lot about it, and more precise results are actually known. But for us, those will be sufficient. Very good. So we are interested in bond percolation in QD. What is it about? It's a very standard model, and it's defined as follows. We start with QD as a base graph. Now we flip a coin, usually a biased coin with probability p for every edge or for every bond. And p is normally taken to be a function of n, n of z, and we will be talking about values of p which are close to 1 over d. So p is actually fastly vanishing, and each edge appears in QDP with probability p and independently of all other edges. So that's actually one of the most studied and most natural models of bond percolation. There's really a lot of names and a lot of glorious results attached to it. I think it started with Saposhenko back then 55 years ago, and then the results of Bursin, Erdos and Spencer looked at connectivity, etc., etc., etc. It's really very well studied model with many papers written about it, even some book basically devoted to it by Remka van Hofstad. So it's really well studied. So from our point of view and from the general point of view, it's asymptotic, which means that we assume the underlying parameter z or underlying parameter n, which is the same, tending to infinity. And we will use the following definition. So an event AD holds with high probability, which we'll abbreviate by WHP in QDP, if the probability of AD, so AD is actually a sequence of events which might depend on the underlying index T. So if the probability of a random sample to fall in AD tends to 1 as D tends to infinity, then we say that this event holds this high probability. So
are you allowing P to vary as D varies, or P
sure,
is
not only I'm allowing it, I'm basically will be working with P which varies with D, and my P will be a bit above 1 over D. So it's a very sparse region. Okay. Very good. So let's continue. Now, what we will be interested in is not exactly phase transition, but close to phase transition. Now, what's known about it? Actually, the basic result, the cornerstone result is here due to IT Commission Semrady from 40 years ago, and they proved the following. So they proved that phase transition happens around P, which is 1 over D. Now, this is actually a combinatorial, not exactly probabilistic talk, and therefore, instead of dwelling a lot on what's phase transition, what's the critical probability, etc., we will mostly working above the phase transition point. But for us, it's important to know where it happens roughly. And IT Commission Semrady proved in 82 that phase transition happens around P, which is 1 over D, which means the following. So let's take epsilon to be a small constant, but a constant. And if we look at the so-called subcritical regime, if P is taken slightly below 1 over D, namely P is 1 minus epsilon divided by D, then with high probability, all connected components of the so obtained random subgraph of QD are fairly small. Now, fairly small means here at most linear in D in size. That's actually a very general result. It's valid for every D regular graph on Q to the D vertices, no matter how good the graph is. Even for best possible expander, you still get this estimate. And that's fairly easy. So the main contribution is, of course, in the supercritical regime. So if you take your P to be slightly above 1 over D, P is now 1 plus epsilon divided by D, which is called, for a reason which will become obvious in a second, supercritical regime. Then with high probability, our graph contains a very large component, namely a component L1 of size linear in N, and this component is unique. And for this reason, and for the sake of analogy with a model GNP and the terminology of Erdős-Renyi, this component is called the giant component. So above the critical threshold 1 over D, if P is slightly above it, by a constant over D, we have a unique giant component. Well, to be more specific, we don't really need much of it, but of course, much more results are known. So, for example, it's known not only that L1 is of size linear in N, but actually the asymptotic order of L1 is known as well. So typically it behaves like gamma over N, where gamma is a unique solution of this equation, which you can see here, or in kind of more accessible description, it's the survival probability of the branching process with offspring, which is distributed like Poisson 1 plus epsilon. Okay? So in this sense, it's very similar to many other models, including GNP. Nothing surprising here. And this is stated in IT Commission Semrady. They, in some sense, didn't really bother to prove it, but they stated it as a probable fact. And it was formally proved by Bolobashko, Hayakawa, and Vucek some 10 years ago, 10 years later. Sorry. And what we can prove is, what's known is also that all other components are very, very small, and all other components are of size which is at most linear in D. So the giant really dwarfs all other components. Now, this result from the paper of Bolobashko, Hayakawa, and Vucek. Now, what's of interest to us is actually not the appearance of the giant component, but its properties. So in some sense, this is combinatorial talk. So we know that these are giant components. It's rather easy to see that this giant component is fairly complex, namely its number of edges is substantially more than its number of vertices. And therefore, you can expect some nice combinatorial things to happen there. And that's indeed the case. And to some extent, we know it, but we would like to understand it much better. So the typical meta problem we are facing is the following one. What are you are in a bond percolation in the supercritical regime in QDP, P is 1 plus epsilon over D. We know that typically there is a giant of linear size. It has substantially many more edges and vertices, and you are interested in its combinatorial properties, like the following ones. For example, what's the diameter of this subgraph? How large is it? And how does it compare to the diameter of the original graph? What can be said about passes and cycles, specifically how long is longest pass and longest cycle in this graph? What can be said about topological properties? How large is the complete minor? What's the genus of it, etc., etc., etc. There's a whole line of questions you can ask here. Closer to the probabilistic ground, if you run the laser random walk, it should be lazy because we are talking about a bipartite graph. So if you run the laser random walk on the giant component, how well it mixes, how long does it take to mix, etc., etc. And I think more or less for all these questions which I listed above, not much was known before our work. So it's really a very nice field to explore, and there's not much known about it, even after our work. We did solve on the qualitative level quite a few questions here, but there's still a lot to explore, and you are most welcome to enter this field and try to understand what's going on there. Very good. Now, it's quite natural if you face an interesting but unexplored model to look for something comparable which is better explored. So in this case, I think the first urge, at least for a person who works on a random graph, it is to look at the supercritical binomial random graph. And there indeed is much more known. I think there we have reached finally, after 50 plus years of intensive research, quite a good understanding of this circle of questions. It all started with Erdős and Renyi some 60 plus years ago. And since then, there has been a long list of results. I'm not implying, of course, that they're trivial by any means. They're quite complicated with some of them, but at least we now have a fairly good understanding of what's going on. And now what's going on? So let me state some results. So it's all this result holds with high probability, so I won't state it each time. So with high probability, there is a path linear in N in the supercritical regimes as a result of White-Commerce similarity from yet another paper of theirs. And the constant in front of N is known to be quadratic in epsilon. And there is by now a fairly simple and accessible proof it's through depth first search. It's known that the giant component there, which is linear size, is expanded by a fairly bad expander. The expansion factor is roughly inverse of log n, and you cannot prove it because you have typically a lot of kind of problematic places. You have bare passes, which are passes of vertices whose degree is exactly 2 of length log n in your graph. You have trees of size log n attached by one vertex to the rest of the graph. So the expansion at mass is 1 over log n. But if you're allowed to clean it a bit, you can find inside a very good expander, an expander of constant factor. This constant depends on epsilon. And if you work hard enough, you can make it proportional to epsilon, and it will be of linear size. It can be derived from a very comprehensive result by Dean, Klubetsky, and Paris about the structure of the giant component. It was derived also by Beniamini, Kozma, and Wormald in their study of the mixing time of the random walk of the giant component. And actually, there is a generic tool of mine which allows to say that every locally sparse graph with bounded degrees contains a fairly large expander, and you can apply it to the giant component to get more or less mechanically an expander of linear size. It's known that the giant typically has diameter which is logarithmic in n, and this is a result of Fernholz and Ramachandran and Riordan and Wormald. And if you look at the mixing time, and if you take it from the worst vertex, it's known to be of order log squared. So that's a result of Fontolakis and Reed, and independently by Benjamini, Kozma, and Wormald. So the dates here might be misleading. I think actually the paper of Benjamini, Kozma, and Wormald is more or less simultaneous to the paper of Fontolakis and Reed. But I think it ties here. You can ask him for more details. Now, what are we proving here? So here's a main meta result. And it turns out that through expansion, you can access lots of these properties, and you can get quite decent qualitative results. And specifically, the main result or the main meta result we are getting is the following one. So we look at QDP, you take the binary hypercube of dimension d, d tends to infinity. You take your H probability P to be 1 plus epsilon divided by d. Epsilon is fixed to be a small constant, so it's a supercritical regime. It's well known that there is typically a component of linear size, and we are researching these properties, and it turns out that with high probability, the giant component L1 itself without any cleaning is 1 divided by poly D expander. Namely, every subset of L1, whether large or small, it can be exponentially large in D, it expands outside by a factor which is inverse polynomial in D. Okay? Now, of course, it's reasonable to ask, maybe you can ask, or maybe you should ask, how poly is my poly? So which power I'm hiding here? That's a very legitimate question, and I will address this question later. In some sense, think about it as a qualitative result. Okay? And we get some concrete power. Towards the end of the talk, I will present you the best powers we can get. They're kind of probably not the best possible, but they are not scary. It's not 10 to the 24 or something like this. But what exactly is poly remains a very good question here. Now you can ask yourself, how ambitious can we be here? Can we get a constant expander as L1 or inside L1? Turns out that's not the case. The best we can hope for is the following thing. With high probability, if you take a set of linear size inside the expander, there will be a set S inside this linear size set V naught, whose cardinality is also linear in N, and the vertex neighborhood of this set inside of V naught will be proportional at most to S divided by D, which means you are bound to lose a polynomial in D, specifically linear in D factor in expansion. So in some sense, to get a 1 over poly D expander is the best we can hope for, but of course you can ask what's the right power of. Now that's the main meta result. And then from this meta result, we can derive meta consequences in a very standard way. So it's well known actually that once you understand expansion quite well, you can get many things about other properties of the underlying graph. And that's the case here as well. So what we get here are the following corollaries. So we look at QDP. P is 1 plus epsilon divided by D. Epsilon is a small constant, which means we are in the bond percolation in the supercritical regime. And we have a giant component. And in the giant component, we get the following consequences. First of all, its diameter is polynomial in D, which addresses and solves a question which was extensively discussed in yet another paper by Bolobashko, Hayakawa, and Vucic from 1994. So we have a path by cycle which is substantially long. Substantially long here means n divided by polylog D. It should probably be much smaller. It's hard to believe that it's smaller than linear n, but we don't know how to prove it yet, at least. And what we get is something quite close, n divided by poly. Now, the mixing time, if you run the random walk on L1 and you take it to be lazy, so the mixing time of the lazy random walk on L1 is typically of order polynomial, which means we mix polylogarithmically in the number of vertices, which is kind of a reasonably good mix. So this answers a very well question, which apparently has been hanging around for quite some time. So I learned at least from Asaf Mahmias, and I think it's stated explicitly in the paper of Gavin Peter from 2008. And actually, if you know the right technique, and these techniques are actually well known and very well used, all these properties can be derived reasonably easily, relying on the expansion results we obtain. So in some sense, expansion is really key to everything here. Very good. Now, those are our results. If you have any questions, you are most welcome to ask. And if there are no questions, let me outline you a proof. Now, for some talks or for some results, actually, the results are much more important than the proofs, and these proofs are frequently technical, and you just apply well-known machinery, etc., etc., etc. So here my feeling is that's not quite the case. I think the proofs are interesting, and you can learn some things from those proofs, and hopefully the ideas here can be applied to different places and different results. So again, I won't be showing you the best possible results because they are quite complicated. You really need to fight and fine tune to get best possible results. What I will outline is a fairly full outline of this poly result. So I will get not the best possible power of D, but I will get some power of D. Okay, so let's start. Try to bear with me because it will be somewhat technical. So first of all, background results we are using. So the first one I've mentioned already, it's the H Isoperimetry in QD. According to the result of Harper, if you take a set S of cardinality M, this set sends outside not that few edges. Specifically, it sends outside at least MD times M, minus M times log, binary log M. So, and for example, from here you derive easily that if your M is at least half of 2 to the D, then you have at least M over 2 edges. So you have at least M edges going outside. Okay, so that's a decent expansion. So another property which is quite well known as well is we will need an estimate, an upper estimate on the number of connected vertex set of given size, and it goes as follows. Suppose I have a generic that's not just for the hypercube. Suppose you have a generic n vertex graph of maximal degree, and you are interested in estimating the number of connected sets of size k in your graph, or even better, the number of trees of size k in your graph, and this is given by the following estimate. The number of trees of size k in such a graph G is at most n, the number of vertices, times ed to the power k minus 1. So that's some kind of folklore result. I don't really know to trace its origin. Someone told me that it appears in the Art of Computer Programming by Knut. I learned it from the paper of Beveridge, Fries, and McDermott from 98. There's this a fairly simple and accessible proof. I think it's quite well known. Very good. The third result we need is fairly simple, but it's fairly handy. And we will be interested in taking a connected graph and cutting into pieces. And these pieces should be of more or less prescribed size. And specifically, we can do the following. So suppose we have a connected graph, and it has more than k vertices, where k is a parameter. And it has maximal degree D, and you would like to cut it into pieces of size roughly k. You cannot quite guarantee it, but you can guarantee that all pieces will be of size between k and kd, and all pieces will be connected. So you can partition the vertex set of a graph into pieces vi. All pieces vi are of size between k and kd, and each piece spans a connected subgraph of gi. So that's actually a result of Asaf Nahmias and myself, which appears in his master degree thesis. So I think that's probably not the deepest result he obtained, but it's still quite nice, and it's widely seen. I see Asaf smiling. Probably, hopefully, it brings you good memories. So delta of G is the maximum degree. Okay, now the approach we'll be using is quite standard. We'll be using so-called sprinkling, and sprinkling goes as follows. So in the context of QDP, so you take QDP, you take your P to be 1 plus epsilon over D, and you want to expose your random subgraph in 2 stages. And you expose most of probability first, and then you put edges with much smaller probability. Therefore, it's called sprinkling. Specifically, you do the following. You represent 1 minus P and as 1 minus Q1 times 1 minus Q2, and specifically you choose Q1 to be quite close to P. So Q1 is nearly everything. And the leftover Q2 is of the order 1 over D, and the constant delta 2 in Q2 is chosen here to be much smaller than epsilon, taken delta 2 to be of order epsilon square would suffice. It's not really important here. If that's the case, you represent your random subgraph QDP as a union of 2 random subgraphs, QD Q1 and QD Q2. That's so-called sprinkling. Now it's very easy because if you look at this comparison, on both sides you have a product probability space, and therefore it's enough to argue about every edge. For the left-hand side, an edge does not appear with probability 1 minus P. For the right-hand side, in order to preclude an edge, you need to preclude it from D Q1, which happens with probability 1 minus Q1, and independently from DQ2, which happens with probability 1 minus Q2, and therefore you have this product here. So every edge does not appear or appear on both parts with the same probability. Okay. So that's a very, very standard trick, and it's used usually you prepare a background and all facilities and all infrastructure in the first graph, and then you just sprinkle in order to give it a final push and to get where you need to get. Okay, since you will be doing sprinkling, you will start with one giant, and then after doing sprinkling, you will enlarge your giant somewhat, and we'll be interested to know what's happened between a giant to a giant, from a giant to a giant. First of all, as I mentioned, the giant before sprinkling, let me denote it by L1 prime. So the giant comes from the first graph. It's for the gamma n, where gamma n is survival probability of the branching process with a distribution Poisson 1 plus delta. That's well understood. Now, if you go from L1 prime to L1, you enlarge it somewhat, which means add some vertices. But the point is, and it's not so hard to prove, that if you look at the pieces which you add when going from L1 prime to L1, there will be quite a few of them. The total mass is linear n, but they're scattered all over the place, and typically none of them is larger than linear n. So the picture will be something like this. It's not so hard to prove. If you use this count of connected sets, you get it fairly easily, actually. So the picture is something like this. You have QD, you have the first giant L1 prime, then you add some a bit, you expose the edges with probability Q2. Q2 is fairly small, so L1 prime gets somewhat larger and goes to L1. But still, if you look at the vertices added when going from L1 prime to L1, you add some vertices, but they are in the scattered speckles all over the place, and every component here is fairly small. Very good. Now, another nice feature which uses substantially the very symmetric structure of the binary hypercube is the following one. So giant is well spread in QD. So what we mean is the following property. We look at the first giant L1 prime, and it turns out that with high probability, every vertex in our graph, not in the giant, but outside of the giant as well, and most of the vertices are outside of the giant. So every vertex is a distance at most 2 in the underlying binary hypercube from the giant. So let me provide some intuition. It's actually not that hard to prove. I will explain the intuition behind it. It's fairly easy to turn this intuition into a formal proof. So let's see. So basically, this idea goes back to IT convolution theory, who used a variant. Okay, so here's a proof idea. So take vertex V. So for every vertex V, if you take 2 steps in the binary hypercube, you get order d squared vertices, which are at distance exactly 2 from it. Now, each such vertex grows a giant with probability which is a constant proportional to epsilon, and they're roughly independent. So the real proof will need to get rid of this approximate sign and to turn rough independence into real independence. This can be done quite easily, and therefore the probability that none of them grows a giant is exponentially small in a d squared. And then if we round again the union bound on 2 to the d vertices, what you get is the statement I stated before. Actually, most of the vertices will be a distance at most 1, but typically all of them will be a distance at most 2 from the giant. So the giant is really very well scattered, and from every vertex you can get to the giant quite easily. Very good. So now let's get into our action. And the first thing we need to do is to prepare our giant, the first giant L1 prime, and we will partition L1 prime into a family script C of connected pieces. And each of these pieces is between K and KD. We can do it for any K by the property P3 of Asaf-Nachmias. And for our case, we choose K to be, that's the right choice, as we will see. It's enough to choose K to be of order D to the 10th. Okay. And now we claim the following thing. So we look at these pieces, we partition these pieces into 2 sets, script C sub A and script C sub B. So A is all vertices in script CA, B is all vertices in script A is all vertices in script CA, B is all vertices in script CB, and let's assume that both pieces are in total fairly large, which means they're at least T in size. Now we claim that we are nicely connected, even if you look at the sprinkled edges which appear as probabilities which inverse proportional to D, even in this sprinkle graph, you have quite a lot of edge joint passes between A and B. How
Yeah,
long is lot?
please excuse me. I'm just checking. The t that you introduced is a new constant, right? It's not something that's related to the previous constant.
Sure. T is actually not a constant. T is any parameter. So I'm arguing that for any value of t, no matter how large or small t is, typically you get for any decomposition of C into A and B, whatever the size of t happens, you have at least Ct divided by d to the 9 passes between A and B. So the larger your sets are, the more passes you have.
Yeah.
Okay. Now, how do you prove it? It turns out that it's not that hard to prove, so let's look into it. So let's look at the vertices which are not on A, not on B, but at distance at most 2 from A. And let me denote this set by A prime. And then let's look at the complement. Let's take vertices outside of A prime, which are at distance at most 2 from B. Now, as we say, giant is all over the place, which means every vertex is typically at distance 2, which means that every vertex of QD will be included into either A prime or B prime. So what we get are two sets, A prime and B prime. A prime contains A inside, and therefore it's at least T. B prime similarly contains B inside, and therefore it's at least of size T as well. A prime and B prime are disjoint by construction, and the union is everything. Every vertex in the world are distance at least at most 2, either from A or from B, which means it will fall either from A prime or B prime by this property of the giant being well spread. Good. Now, so we know that the sets A prime and B prime are of size T. They are complement of one another, and therefore, by the isoperimetric property, there are at least T edges between A prime and B prime. Now, what you do is you take such an edge between A prime and B prime, and you extend this edge to a path of length at most 5 from A to B in QD. So you do the following. So here you see the sets A and B. They're encircled in sets which are larger A prime and B prime, and A prime and B prime is a decomposition of the whole vertex set of QD. Now, if you have an edge AB between A prime and B prime, go 2 steps back from A to capital A, go 2 steps back from B to capital B, and you get a path of length 5 from A to B. So for every edge crossing between A prime and B prime, and there are at least T such edges, there is a path, and this path is of length 5. Now, it could be that this path, such a path, intersects some other passes, but the intersection can be very massive because we have a d-regular graph, and the passes are of length d to the 4, and therefore every such path intersects by at least h and h at most d to the 4 such passes, which means we take t passes and we divide this by the intersection, and we get at least ct divided by d to the 4 edge joint passes of length at most 5 from A to B, not in the random subgraph, but rather in QD itself. So we have a lot of material, and we will be able to sustain quite a few of those passes when we do sprinting. Now, each such path survives, it has at most 5 edges, and therefore it survives into the sprinkled graph with probability at least Q2 to the power 5, which is of order 1 over d to the power 5. We have many of them. They are edge joint. That's how we constructed them, and therefore we have a binomial random variable with expectation of order t to the 9, t divided by d to the 9, and therefore by concentration probability that you get half that quantity is exponentially small in t divided by d to the 9. Okay, and now we need to run the union bound, which means we need to look at all partitions. How many partitions do we have? So the number of partitions is at most 2 to the d divided by k. So the pieces are of size k, and therefore the total number of pieces is at most 2 to the d divided by k. And we need to accumulate t vertices. Each piece is of size t. So the number of ways to accumulate t vertices is at most, you need to use at most t divided by k pieces. So altogether you get a binomial coefficient, which is roughly 2 to the d divided by k. Choose t to the k, which is at most 2 to the dt over k. So you run one huge positive exponent against one huge negative exponent, and you want to win, which means you want the negative exponent to win. And for this, it's enough to take your k to be d to the 10. So that's the justification for our choice of K. Very good. So we are well connected, and now let's put it all together and let's see what can we say about expansion. So our goal will be to argue about edge expansion of the expander after splitting. So let's take a set S or inside L1, and let's denote cardinality by S. Now we classify the vertices of S into three types: S1, S2, and S3, and we do it as follows. So we need to estimate the edge expansion, and from the edge expansion we will derive immediately and cheaply vertex expansion. So how does it go? There are three parts, or there are possibly three parts in S, and they are as follows. There's a part S1 of vertices in the giant, but not in the old giant. Okay. There's a part, now the two remaining parts are in the old giant, and they are classified into two types. There are vertices which are in pieces. We remember that we decompose the old giant into pieces, and some of these pieces are fully covered by S, and some of these pieces are split by S. We take vertices in the split pieces and we put them into S2, and we take the vertices into full pieces and put them into S3. Now it could be that some of these pieces are empty, but at least one of them is non-empty. Okay, and we denote by small s Si the cardinality of S3. So if we need to depict it, the picture will be as follows. Here's a larger new giant in gray, and beside it is a smaller old giant in yellowish. And S1 are guys in the new giant, but outside the old giant. S2 are vertices in S which are inside the old giant, but in the pieces which are not fully covered by S. And finally, S3 are vertices in pieces fully covered by S. So that's the picture. Okay? And each of these types will contribute in its way to the edge boundary of the set S. Okay, so let's go piece by piece or type by type, and let's see what can we get there. First of all, contribution of S1. Now, if you look at a component in the old new giant, but not in the old giant, if this component is broken by S1, which means if it has vertices inside of S1, but also outside of one, because since we are talking about a connected component, there will be at least one edge in the boundary of the set, because you need to connect inside this component. Now, if you take a fully connected set, that's not bad either, because this fully contained set, it's still a part of the giant, which means there is at least one edge emanating from it and going somewhere. Either this edge is in the boundary of S. If it's not in the boundary of S, the only choice for it is to go inside the old giant and to land in S2 union S3. So altogether, you get that either the partial of S is at least CS1 divided by D, since all components are of size at most D, or you force the union of S2 and S3 to be large enough. So in the alternative case, we know that the number of edges between S1 and S2 union S3 is at least of the order S1 divided by D, and since the maximum degree by definition of the subgraph is at most D, we get the union of S2 and S3 is of cardinality at least S1 or order S1 divided by D squared. Okay, so let's look at the second type. So the second type is the pieces, the vertices inside the old giant, but in the broken pieces. So here we are in a good shape as well, because we have broken pieces. Each broken piece, by virtue of it being a connected component before, gives at least one edge to the boundary of S, because you need to go from one part of the broken piece to the other part, and the other part is outside, you get at least one edge. Now the pieces are of size at most KD, which is at most of order at most D to 11th, and therefore you get that the contribution of the second type is at least as large as constant S2 divided by D to 11. Okay. Now the final part is pieces which are inside the giant and which are in the decomposition pieces fully covered by S. Okay. Now, what do we know about them? We know this connecting statement about slicing and connecting. We know that if you take a collection of full pieces inside the decomposition, they send lots of disjoint points outside. Now, how a lot is a lot? We get here S3, which is the cardinality of these full pieces, S3 times constant C divided by D to the 9. edges on passes which leave S3 and go elsewhere in the old giant. Now, it could be the case that some of these pieces get stuck in S2, but you cannot have that many of them because the capacity of S2 is at most ds2. Okay, you have at most S2 vertices, each one of them has degree at most d, and therefore you have at most ds2 edges or passes ending up in S2. But the rest of them should go outside of S, and therefore the contribution of S3 to S is at least as large as CS3 divided by d to the 9th, the number of edges and passes, minus the number of those which get stuck in ds2, which is minus at most ds2. So the picture is like this. You have this old giant, you have this full piece S3, now, and you have pieces S2 which are inside the giant but broken by the decomposition, and S1 outside the giant. Now, I look at the edges of the passes emanating from S3. Some of them end up in S2. They are no good for us because they don't contribute to expansion. An edge going from S3 to outside of S2 inside L1 plane is a good edge, and we count those. Now, we also have long passes starting in S3, like this arc pass here, and ending up in L1 prime. They might pass through S1. They actually even might pass through S2, but eventually they end up in L1 prime, and this edge will contribute to the boundary of L1 prime. Okay, so this justifies the self-contribution. Okay, let's do the final count. So, and let's go case over case. So, if S1 to remind you is the vertices in the new giant, but outside the old giant. If we have many of them, if they at least have the vertices, then either we have an edge boundary of size at least CS over D, and we are very fine here, or it forces S2 and S3 to be large enough. If S1 is large, then we force S2 and S3 to be large enough. And otherwise, S2 and S3 is large enough. Okay. Now, the second case is S2 plus S3 is fairly large, of size at least CS divided by D square, and S2 is small, which means most of it is occupied by full pieces, but then we get this estimate. The partial S, as I said, partial S is at least CS3 divided by D to the 9 minus D squared. C2 is fairly small, and you get CS divided by D to 11th, and we are fine as well. We are getting S divided polynomial in D. And the final case is when S2 is substantially large, broken pieces contain many vertices. Each broken piece contributes an edge. You cannot have few broken pieces because the broken pieces are, all pieces are fairly small. So altogether you get a partial S is at least CS2 divided by D to 11, which gives you CS divided by D to 23. So if you combine all these together in all these three cases, you get that the edge boundary of S is CS divided by T is 23. And then the cheapest way to get from edge boundary to vertex boundary is to recall that the subgraph has maximal degree D, and therefore if the edge boundary of a certain set has cardinality T, then the vertex boundary has cardinality at least T divided by D. So all in all, you get that for every set S of cardinality S, its vertex boundary inside the giant is of size S divided polynomial in D. Okay, so the power here is 24, not something to brag about. So in some sense, it's a qualitative result. Okay, so we are getting S divided polynomial in D. Okay, but that's the result. Any questions? Okay. Now, as you can imagine, and if you followed it carefully enough, you might notice that there's really a lot of places in this sketch where we can do that. So let's try to tighten all screws. I won't do it here, but I just state you what we are getting. So if you really look carefully at all those proofs and try to optimize them to the maximum degree possible, or at least to the maximum degree which you're able to do, then you can get a lot of mileage and you can get much better results. And those results I can state indeed. Those are really quantitative results, and there's something which one can try to compete against. So if you do it more carefully, then you get the following results. So we are in the supercritical regime in bond percolation on the binary hypercube. QDP, P is 1 plus epsilon over D, epsilon is a small constant. So we take the giant component, which is of size typically proportional to the D and linear in the number of vertices, and then the following holds. So first of all, the giant component itself is not that bad an expander. The exponent we get here is not d to the 24, but d to the 5th. So the giant itself is a constant divided by d to the 5th expander. So it's not as good as perhaps the best possible 1 over d, but it's already much better than 1 over d to the 24. Secondly, you can do even better. Actually, inside this expander, you have a much better expander. Much better is of order constant d squared divided by log d. You can find an expander on nearly all the vertices, 0.99 of the vertices, and the expansion factor here is not 1 over d to the 24. It's not 1 over d to the 5, but rather of order 1 over d squared log d. So that's already pretty decent. There's a huge expander there, which is quite distant. And from this, you can easily derive using standard machinery that what we get here is a cycle of length n divided by d squared log d. Not quite linear yet, but it's already quite close. Okay. More results is so in the same regime, supercritical bond percolation on the binary hypercube. L1 is the giant component. So the first result is about the diameter. If you do it carefully enough, then we can get the diameter of order d cubed. So to remind you, the diameter of the giant before percolation is d. Here we get d cubed. It's a very nice question what the truth is. Presumably it's smaller than d cubed. Whether it's d or something larger, it's probably much closer to d than d cubed, but how close it's to d, I'm not sure I'm willing to bet. And if you look at the mixing time, and if you do it carefully, so it turns out that the mixing time is with high probability, if you run the laser random walk, is of order d to 11. It's polynomial with some decent power. Now, those are our results. In terms of open questions, the picture here is kind of more or less self-explanatory and obvious. Those are the results I presented you in 2 previous slides are already quantitative results, and it would be quite nice to beat them and to get better bounds. For example, what can we say about expansion of large sets? We know that no matter which subset of L1 we take, the expansion cannot be better than 1 over d, but perhaps we can make it 1 over d. Maybe you can choose carefully a subset of L1 and to see that the expansion inside the subgraph spanned by this set is of order 1 over d. This would be quite nice. So this question, the next one, is kind of quite embarrassing for a combinatorial person. It's more or less obvious that the circumference here, which means the length of the longest cycle, should be linear in n. Unfortunately, we don't know how to prove it. The best result is our result, which is n divided by d squared log d, and it should be much better. It would be quite nice to prove it. Now, what can be said about the diameter? And maybe the diameter goes all the way down to linear in d. This would be quite nice to prove. In terms of the mixing time, it's hard to believe the mixing time is d to 11. The best lower bound you can get, which is quite trivial, is d squared. More or less for the same reasons you get log squared n for the random walk on the giant component in GMP. And presumably it's much closer to d squared than d to 11, and it would be nice to improve it. And another possible direction or method direction, if you wish, is to take these techniques and to apply it to other random subgraphs, to percolation on other subgraphs. I think it's kind of obvious that if you take not a binary hypercube, but some maybe lattice or some other hypercubish base graphs, then you can get something similar. But still, this proof uses in a very substantial way some of the properties of QD, which are not available everywhere. For example, the symmetry of QD, etc., etc. The fact that the giant is all over the place, which is not necessarily available everywhere. So it's not a universal recipe, but it's probably much more general than what we get here. So that's one possible horizon in this line of research. Very good. Let me stop here.
Thank you very much, Michael, for this nice talk.
Thank you.
Please. I'm not sure if you said it, but I had a question. So do you have a conjecture for the expansion factor? So you have d to the 5, and do you hazard a guess for the exponent?
Yeah, so the best we can hope with
1 over d.
So in some sense, the question is not well defined, but it could be the case, just like in GNP, that the graph itself, the giant itself is fairly bad expander, but we can clean it. So presumably we're asking about the cleaned subgraph, and for the cleaned subgraph, the best we can hope to get is 1 over d, and it could be the case that the answer is indeed proportional to 1 over d. There is a fairly substantial subgraph inside the giant whose expansion factor is proportional to 1 over d.
All right, thank you. And another question, you didn't look into this aspect, but just to ask you, the dependence on epsilon, would your techniques be good for that as well?
Well, that's, some say it's we are so far from the truth here in terms of power of d that we didn't really bother to look into the dependence on epsilon. I think it would be kind of, once we figure out what's the right answer for in terms of power of d, we can look at epsilon. Another kind of maybe a question alludes to the following. So we can look at our results. Our results are proven, at least and stated, for the strictly supercritical regime. They survive to some extent, some rather limited extent, if you take your epsilon to be tending to 0, which means you are kind of slightly supercritical. So that's also a legitimate question, and I think some of them survive. We can probably take our epsilon to be some small negative power of d, but not all the way to the limit of this.
Yes. Okay. So they're relevant techniques. Very good.
Sure. I mean, I think it's a very legitimate question, at least understand the qualitative level. On the qualitative level, the slightly supercritical regime, which means to allow epsilon to tend to 0, maybe relatively slowly with d.
Yes, that's fine. All right. Thank you very much. There was a question in chat. Rani is asking whether prove linear diameter for any particular value of epsilon, maybe epsilon equal 10.
This we haven't tried. Not so clear, because the standard way to prove, well, linear in Z means logarithmic, and the standard way to prove a logarithmic diameter is to argue the expansion, correct? Because if you have a nice expander, you expand by a constant factor each time, and you are there. So we don't have it yet, and therefore I'm not sure we can do it for epsilon, which is equal to 10 or 10,000. But it's very plausible.
Other questions? Okay, if not, then let us thank Michael again for this great talk.
Thank you.
And we meet again in 2 weeks, and I'll send an announcement. Thank you very much.